All right, so last class we did what is called similarity transform. Then the next one, okay, which is a combination of uniform scaling, rotation, and translation. So another thing, right, which is of interest is what is called shear. So we'll just see, right, how this transformation looks like. So you have like xt, yt, and then if it's an x shear, right, you will get 1 k 0 1 xs ys. So what this means is that your xt, right, is going to look like xs plus k times ys, whereas your yt is equal to ys. Okay, this is something that you can see when you're traveling in a car, and if you look at a zebra crossing, and so the scene kind of sets itself up in a particular way, in the sense that the normal sets itself up in a particular way. You're traveling in this kind of direction, the normal of the scene is like this, and your motion is along x. So you'll get something like this. So what this means is, right, if you had a square, right, like this, then what this means is that you can get a shear like that. Okay, or if it is the other kind of shear, then it will look like this. I mean, depending upon whether the shear is along x or y. Okay, this is called the shearing operation. So the other kind of shear is that this becomes 1 0 and that becomes k1. Now, and this is like xs ys. So in this case you get like xt yt. So xt is equal to, what is it, xs, right, and yt becomes equal to k times xs plus ys. Okay, so yeah, so which way the shear occurs, right, depends upon how we are moving, but typically, right, this is what will happen. Actually, right, this is all a special case of something which is more general. What's called an affine transformation. And there is something more general than affine, right, which we will see shortly. But okay, this center should be right there. Okay, the center doesn't move. I'm just going to say tilts like that. So the affine, right, is more general, and it looks like xt yt. Okay, and by the end of this class, right, you should be able to stitch images. For example, you should be able to take your camera, capture pictures, and be able to stitch them. So xt yt. So this looks like a, b, c, d, xs, ys plus dx, dy. So as you can see, right, all the others that you saw previously were all kind of special cases of this affine. So if you take a, b, c, d to be of a particular kind, then right, you can get the rest. But sort of a general transformation is affine. And what it kind of preserves is that parallel lines remain parallel. Angles are generally not preserved. Angles are generally not preserved. Preserved, and preserves ratios of lengths of parallel. Preserves ratios of lengths of the parallel segments. I mean, if you have a general affine, of course, in some cases you may still end up keeping the angles and all intact. I mean, that depends upon how the ABCDs are, because the previous ones are all special cases of this affine. But in general, if you have like ABCD, in general, if you have a general affine transformation, then all that you can expect is parallel lines remain parallel, angles may not be preserved, See, for example, right, so in the, in the earlier example when you had a shear, right, I mean, initially the angles were all good as right angles, but the moment the shear happened, right, the angles changed. And then the preserves ratios of lengths of the parallel segments. Okay. There is something even higher than affine. Okay. But then prior to going that, right, we'll just look at what are called homogeneous coordinates. I mean, there is a way to see, if you see, right, I mean, the way I'm kind of say writing this is that in some cases I'm able to write it as a transformation on say xs comma ys, but in some cases, right, I'm not. Like for example, a b c d into xs ys plus tx ty, right, it doesn't look like a, a direct transformation on, let's say, right, xs comma ys. It looks like I have to do something and then plus add something, right. So it doesn't look very, say, elegant. Okay, there is something called a projective space. Okay, I mean, there's a whole area out there, okay, which is called a projective geometry. Idea is not to go into the details of that, but just to take, right, elements from there which are actually relevant to us. And one of the things that is taken from a projective geometry is what are called homogeneous coordinates. So, for example, the coordinates that we deal with are called actually heterogeneous coordinates, the ones that we normally use inside a Cartesian space. But then in a projective space, these are called homogeneous coordinates, and one can kind of go from the homogeneous coordinates to your say heterogeneous coordinates. And the way to interpret it is, if you are say heterogeneous coordinate, or what you normally use in a Cartesian space, heterogeneous coordinate, right, if it is, let's say, x y, okay, if it is like x y, then the homogeneous coordinate can is just you just have to add one more sort of a dimension to it, call it x y 1, or in general, right, it can be alpha x, alpha y, alpha not equal to 0. We will see later a little bit more about what these coordinates are, and okay, the last one is alpha. Okay, what this means is, if you scale the first two coordinates by the last one, right, you should be able to go to the heterogeneous coordinates. So you can think of this as a sort of points on a line like this, right, and then a projection, right, of these points. So for example, right, every I mean, these are called homogeneous because all of them say represent the same, right, I mean, x y comma 1. I mean, if you kind of think about it, right, so it's like x y 1, right. So they all kind of, I mean, they all kind of look the same in the sense that, except for a scale factor. It's like saying that if you travel on this line and if you were to project them all here, and if you had your x y axis like this, right, where let's say this is your z, and this point is like x y 1, okay, this z, this x, this y, then all the points on this line, okay, if you kind of map them onto that plane, right, they would all map to the same x y comma 1. We will see this in more detail later, but for the time being, right, just kind of remember that if you are using the homogeneous coordinates, and if you want to go to these heterogeneous coordinates, because finally when you do image transformations, right, you have to come back to a Cartesian space. All that you need to do is the even third coordinate, whatever it is that you have, if you divide the first two by the third, that you will come back to your original space where you are operating. Okay, for the time being, okay, this much is enough. When we will kind of make use of this later. I mean, it also, there are other things to this, in the sense that, right, I mean, points like points at infinity and all, right, which in a heterogeneous coordinate, right, I mean, infinity is not really a number, right, in that sense, whereas in a homogeneous coordinate you can write point at infinity as is x y 0. Okay, so you can still use finite numbers to tell that you have a point at infinity, and so on. So it helps, so in terms of geometry, right, it helps explains points at infinity and all, vanishing points as they are called. But right now, okay, we will not kind of get into that. For our courtesy, this one, a temporary, this one, the purpose is want to know how to write these homogeneous coordinates, because if you know this, right, then I can go back and rewrite many of the things that I wrote, but now in a kind of much more elegant way. For example, right, if I go back to say translation, okay, because we need this prior to going into a projective transformation. So for example, translation, right, if you remember, we had simply x t y is equal to x x y s plus t x t y, right. Now instead of that, what I am going to write is, I am going to write this as x t y t, extend this as a dimension by 1, and then I am going to write this as a kind of a 3 cross 3 matrix, and then I am going to write my source as xs ys1. Okay, in this case I know that the last coordinate is 1. In general it need not be, but in this case I know. So now for example, right, so now if you had to write this, how would you write it now? How would you fill up this matrix if you have to represent a translation? It will be 1 0 tx 0 1 ty 0 0 1. So if you see, right, this is like xt is equal to xs plus tx, yt is equal to ys plus ty, and 1 equal to 1, right. So you see that exactly what we had earlier, but now it looks like a direct transformation. And I mean otherwise, right, if I had asked you to write xt yt, and then I had, what did you have, xs ys plus tx ty as a kind of as a 2 cross 2 operation. Can you write this as a 2 cross 2 matrix multiplying xs ys? You cannot write it, right. So this homogeneous coordinates allows that flexibility. Then this interpretation becomes much more easier. It looks like, you have the source coordinates, you just want to apply on them, and if it turns out that let's say that if this last row is not something like 0 0 1, in general it need not be, then in that case whatever is this number that you get here, okay, if you use that number and scale these top 2 coordinates, then you're back to this heterogeneous. Okay, just have to remember that, because if you want to go back to the original space, that's like xy1, and for that, right, you should just scale. I mean, if it so happens that the last number is not a 1, in this case it turns out to be 1, therefore you don't have to do anything, you directly get your xt yt. If that is not happening, then you should scale it. For example, if you had to do a rotation, right, a 2D rotation, how would you write it now? You will again write xt yt1, then it is going to be xs ys1, then you will have like cos theta, sin theta, minus sin theta, cos theta. Know this one translation 0 0 1, right. Of course, this even in a kind of a 2 cross 2 you could do this actually, even there you could write this as a 2 cross 2 times xs ys, but just that, right, but translations you couldn't write at that time, but now you can write everything in this form. Rotation, and then if you think about what was that, scaling, right. So scaling would be like xt yt1, and then xs ys1. Then you have like, let's say your scale factor is a, then let's say 0 0 0 a 0 0 0 1. Okay, that would be scaling, and then you can also have a combination of these transformations, right. It depends upon the order in which you're going to apply them. So for example, you can have xt yt, let's say 1, and I can think of these 3 cross 3 matrices. So if you have a similarity transform, I can have a scaling, I can have a rotation, I can have whatever, a translation, but then if you change the order, then again the entire thing will change. Okay, so this matrix operations do not commute. Okay, so it depends upon what you're applying first, right. So for example, if this is your xs ys 1, and if you say that this translation, suppose, right, this rotation and this scaling, then it means that you're first applying a translation on xs ys, followed by a rotation, followed by a scaling, right. And this last coordinate you have to watch out for. Okay, it depends upon what's happening on this right hand side. So now if you now for example write affine, right, if you had to write, how would you write that now? You have xt yt1, and then you will have xs ys1, and then you have some like a b c d e f 0 0 1. Right? That would be an affine, or you can write the c and f as tx comma ty if you wish. Okay, and so what this really means is, right, in an affine you've got like 6 unknowns, and all this right goes back to how we are able to solve for an image transformation finally. Right? Why are we doing all this? Simply because if you had to do a data augmentation, then we should know how to say generate or synthesize an image. If you are trying to align 2 images like in a kind of a panorama where you want to stitch, then you need to know what is the transformation across them, which means that right, if you know a priori that it's an affine, right, then you need to only solve for 6 unknowns, but in general if you don't know anything about it, then it has to be higher than this, right. We do not know what motion happened, but if somebody gave you a priori information that it's only an affine, then you can restrict yourself to 6. If they say that it's only a pure rotation, then you can just restrict it to 1 if it is in plane rotation. Okay, and this R, the form of R will change, okay, depending upon whether it is okay, yeah, right, which is what I'm going to say going to come to next, which is actually a projective transformation. a projective transformation, or it's called a planar homography. A planar homography. There is also something called a rotational homography, right, which we will see at the end. But then a projective transformation is the most sort of general. Okay, and this projective transformation is again a 3 cross 3 matrix, but which can be only estimated up to a scale because of the fact that these homogeneous coordinates, right, you know them only up to a scale, right. So if you think about it, you will have like xt, yt 1, and you can write this as okay, we will just use h11. So this is a homography matrix. Okay, so the standard notation is h11, h12, h13, h21, h22, h23, h31, h32, h33, multiplying xs, ys1. Okay, and now, right, this in general, I just multiply this by lambda because, right, there is no guarantee that this last number will be 1 now, right, because of the fact that this could come out to be anything, right. So I will just say lambda, okay, which is also the reason why this matrix itself has only 8 unknowns now, because the matrix can only be found up to a scale factor. Okay, so you have actually 8 unknowns, even though there are 9 entries in that matrix, right, you can only find it up to say 8 unknowns. Okay, so this is the H matrix. This is a planar homography, and you know, actually, right, this actually relates to the say right now the way, right, we are actually thinking about it is, if I had right 2 images, and if I wanted to find out what is the relation between the two in general. Okay, and this comes from a full 6D motion. Okay, 6D motion. What that means is I could sit at a place. Okay, so for example, if I am at point C and I want to go to say point C dash, then I can translate along, what is it? So this is like x. I can go like tx, I can go like ty, I can go like say tz. Okay, I am allowed. So this camera. So this is the camera space. Okay, all these coordinates that we are talking about are all on this are all on the image space, right? When I write xt, yt and all, this is not in the 3D world, right? I am talking about what's happening on the image plane. But all of this is happening because the camera is moving in a certain way, right, and the scene is kind of say directed at the camera in a certain way. Again, it's an interplay between the two. And what this means is that if I am here and then if I want to go to C dash, I can go through 3 translations and I can have 3 rotations. Rotations means I can have the whatever, right. I mean, I could actually spin about the x axis, I could rotate about the x axis, or I could rotate about the y axis, or I could say rotate about the z axis, right. So the z axis is what aligns with the optical axis. So your in-plane rotation is typically this, about the optical axis. Anything else that you do will cause an out of plane rotation. I mean, something like this, right, will cause an out of plane rotation. Or if you, what is the other one? This way, right. So if
you do out of plane rotation, then the image plane itself you won't be in the image plane.
No, it's like this, right. See, your image plane is fixed, right. So what this means is that what kind of an image will get formed. See, for example, right, if your camera undergoes a rotation, let's say, right, and then you go here, then the idea is that how do you relate the image which you get in this view to this view? A projection? Yeah, but we need to be able to show what is going on, right? I mean, we know that all of these have a role to play. Now, how they actually come into the picture, right? You're doing a rotation, 3D rotation. You're doing 3D translations. This homography helps you to relate the 2 images finally. Because, right, I mean, see, eventually what do you want? You want to be able to relate images, right? You see, you may not even be interested in the camera motion. Actually, most of the time you may not be interested in what is the camera motion. Right, who bothers about it? For example, when you stitch the images, right, do you think that you will be very interested in knowing how the camera, what motion the camera went through? You will be only interested in aligning the images. See, this homography, it's wasn't the camera homography, yeah. No, what I am saying is the camera motion, like this tx, ty, tz, which is in the 3D world, and the rx, ry, rz, that may not be specifically of interest to you, right? Okay, that's what I mean. That means those 6 unknowns that are actually sitting there, you may not be interested in them, or you may not be even interested in how the scene normal is. See, for example, if you take a unit normal of the scene, right, you've got to see 2 unknowns there, right? And the third thing is how far away is the scene, right? None of this you may be interested in. All that I know is anything like that can happen. The optical axis, so the scene could be completely fronto parallel. It could be inclined at some angle. I could be moving arbitrarily, right? You know, in a kind of I could be having an arbitrary 6D motion, but I may not be at the end of the day interested in knowing how much I moved by. My interest is only in being able to relate the images, because all that I have are feature points, right? Finally, I have an image here. I have an image here. If I can get my feature correspondences, I should be able to align the images.
The change of images
Due to motion. All of this is because of motion, by the way. Everything that we have said is because of camera motion. None of this is anything other. This is not a barrel distortion or a distortion of the lens or anything. This is all pure camera motion.
then how can we relate to images without considering the camera motion?
You don't, I will show you now, no? Okay, so yeah, so the idea is that in general, see, it's like this, right? I think, you know, what you're trying to ask me is, should I not know how the camera moved or something? No, the whole idea is you don't need to know. In fact, this homography matrix itself, right, this has a form. This comes as some, what is it, R plus 1 by D, T n transpose, K dash, okay, K inverse. Okay, this is I mean, right, I am not showing all this, but this is the homography actually. If you have a planar situation, right, what this means is you have a normal for the plane, which is this n. You have a translation of the camera, which is actually, you know, a 3D translation. Then this vector, if you take the outer product, right, this becomes a 3 cross 3 matrix. Then there is a rotation, which could be a combination of Rx, Ry and Rz in some sequence, and then right, you have what is called an intrinsic camera matrix, which is K. So there are various factors here at play. Okay, there is something called the intrinsic, which is the camera matrix, which is K. I'll talk about it. I'll talk about it right in the next class, right, how you arrive at the camera matrix and so on. But that is again there. Okay, it doesn't mean that it's not there. The camera intrinsics also matters. Then there is an R and T, right, which is this rotation and translate, which is supposed to be extrinsics. So these are extrinsic parameters because they don't belong to the camera. You just depends on how you move. K is something intrinsic to the camera. It's like saying, where the center of the camera is it kind of deviated? Are the axes of the camera exactly orthogonal? Is there a skew? All of that. So that is all related to the camera per se. R and T are not related to the camera. That's why you call them as extrinsics. But then the idea is not to kind of go into this. The idea is not at all to go into this. We don't want to go into that. Okay, that's what I'm saying. Without going into that, you want to be able to relate images. Okay, that is the idea.
Degrees of freedom of motion and the two shear.
No. Actually, I didn't want to get into this, but it's more or less like this, right? See, for example, I mean, the 8 unknowns, right? If you want to think about it, it will be like, 3 for R, 3 for T, and then say 2 for N, because it's supposed to be a unit normal. So you have 2 unknowns for the normal, 3 for the translations, 3 for R. I mean, if you want to think about it that way. But the whole idea is not even to get into, see, it's not like we have got an H and therefore we want to go back and work out R and T, and we are not even interested in that. The inverse problem, there is something called, finding out the camera motion given the homography matrix. We don't want to get into that. It's like saying, given this, right, can you arrive at this? I mean, that's a harder problem. We don't want to even get into that. Panorama stitching does not involve any of that. Okay. Now, what this means is the following. Okay, now I think we spent too much time on that. I wasn't planning to spend that much time.